No here.
Let's do this one, and then we'll go back to number 1. A and B have the same exact work. It's just that in A, you're assuming they're 0.5, and B, you know what they are. So here, Z is 2.575. P hat and Q hat are both 0.5, assumed to be. And the error, they told me, is 0.03. What do you guys get for that? This is right. What do you guys get? Anybody? Some of you guys lean on. I'm going to tell you.
1842.
Yeah. So you get 1841 point. Doesn't matter. You round up to 1842. So that's a decent number of people.
You're saying with 1,842 people, you could say anything with a confidence interval within 3%, regardless of the size of the population.
So again, there are those conversion factors that we're not taking into consideration. It's sort of like when you learn, I know most of us haven't done this, but when you learn the first level of physics, somehow all your ropes are massless and your tabletops are frictionless so that you can learn the math. And then the next level of physics, you start to worry about, well, that rope really has some mass to it and the friction on the table is something. So you start bringing in some corrections to the basic foundation. So this is stats 1, we do a basic foundation. There is a correction based on if my population is relatively small, especially compared to my sample size, that comes into play. We're not going to do that correction. We're going to assume our tabletop is frictionless.
It just seems like there ought to be one for each really big. Like, this formula is the same regardless if there's 1,000 people in that stats class or if there's 1 billion.
Oh, you're worried about... So theoretically, we're dealing with an infinite population. So this is the answer for an infinite population. Yes?
This might be a dumb question, but for 99% confidence, how can we get 0.995 on the graph?
Oh, I love it. Okay. This is beautiful. This is beautiful. Let me do it up here since I got my camera that way. All right, you guys ready? That z-score chart only understands areas that are below a z-score. That's all it tells me. That's all I can give it. Confidence intervals are not that. So you're never going to find a confidence level in the z-score chart itself. So if I have a 99% confidence level, like that, right? Is that cool? What area is actually below this z-score? What area is out here? 0.005, right? So what area is below this z-score? 0.995. I like it. It's because confidence intervals are the area around the middle. It's not how the chart's built. Chart's built just to understand areas below a z-score. That's why we look this up. You could look this up instead, because it's going to be negative number, positive same number. So it doesn't matter which one you find. Good point, though. I like it. I'm going to have to say that a few more times. But that's a good catch. Be careful about that. So now I do all the same exact work, except I know what p hat is. And I know you guys have heard this phrase, preliminary study. The one reason you do it is so you get a better estimate of how large a sample you really need. So what is p hat? How do I calculate p hat for this problem?
31 out of 42.
Yeah, 31 out of 42. And what do you guys get for that? 738? So then Q hat is 262. You guys with me? So now we don't have to guess anymore. We have an actual little study that was done, a little preliminary study. I got values for those. Now I do the exact same formula. The difference is I know P hat and I know Q hat. And now my N is going to be decently smaller. Oh shit. Can't do a shortcut job. What do you guys get for that? Mac, well, we lost a few people that we had to talk to. I get 1,424.5, blah, 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 so I get 1,425. So somewhere between 20 and 25% less sample size needed. That's good. That would save time and effort. Right? So that's one reason we do preliminary studies. Nowhere near the main reason we do them, but it's one little reason. Okay, I like it. I like it. Okay. Yes?
So there's no conclusion statement for these types of problems?
Not really. I mean, you could say, you could put units on this, students. But I'm not going to be overly picky on that. Trying to figure out what the sample size needs to be. I like it. Yes, sir.
So if we were polling the professional district, we could poll 50 or 100 people, figure out roughly what the percentage is going to be, use that to figure out how many people to poll in the field study.
To be within a certain error. So if you want to be able to tell people we're within 3%. You don't want it to be 6 or 7%. So you want people to trust it a little bit more. You can do exactly what you just said. And make the error 3%, figure out how large of a sample you're going to need. And then what you normally do is take a little bit larger sample just to be careful. Yeah. Okay, maybe. Because if you tell somebody, yeah, it's going to be 40% want this, you ever take 11%, like, screw you. You don't have a clue. So you want to get a feel for how large a sample you need. Is it feasible? All right. We got to do this one. This is your standard one. What do you get for the percentage, the p hat? Yeah, 704. So what's Q hat? 296. I like it. What's N? 652. Is this normal enough? What's NP hat? That's what it has to be. What is it? If you don't trust me, just take 0.704. That's p hat. Multiply by 652. You're going to get 450 something. Because we rounded this, right? I can just go ahead and see it. That's the number of successes right there. That's at least 5. What about NQ? It's going to be the rest. 193. That's at least 5. Yay, check. That means I could do the problem. So some of you guys are like rooting for that to be less than 5. Don't blame me. I want 96% confidence just to be a jackass. So you have to draw the picture. You have to do it the old-fashioned way. 0.96. Right, this is the way you do it when it's not on that little baby chart. And again, if you're still not sure what I mean by a little baby chart, if you go to the positive z-scores at the very bottom, there it is, 90, 95, 99. You know what those are. Here's the z-scores for those confidence intervals. 96 ain't on there. Ah, shit, Jeff. So what am I going to look up in the chart? Yeah, I can either look up 0.02 or I can look up 0.98. They're both going to give me that same number. The plus or minus is just up and down. So the closest I get to 0.02 looks to be right there. You guys see that? So on 2% below, so it looks to be negative 2.05. So 2.05. Oh, so there's 96% inside. How much is outside? 96% inside, there's going to be 4% outside. So how much is on that one side? Yeah. Beautiful. Okay, maybe. And now we have everything we need. We have all this stuff. We have everything we need for that. So we plug all that stuff in. Here's my best guess. Give or take. This many of these. Figure out the error first, always a good idea. Let me show you. All right. Let me just show you a little tiny itty bitty shortcut. 2.05 times square root. Store that. Store it in x. Bam. Then you can do 0.704 minus x. Bam. 0.704 plus x. Ooh, it's not that big of a deal, but that's good to use that memory location. If you don't like what I just did, it don't matter. Just subtract that number, add the number. Okay. So then I get my little interval I can make is oh, I forgot to put my little error down. Write this out. What was the error? Where are you at? There you are. 0.0366. Then I get 0.667 up to 0.741. Okay, I like it. And that's just to give yourself the little intervals. There it is. There's the interval. And then a little more important than that is explaining what that interval means. So we are 96% confident that what? The interval. What? 66.7% to 74.1%. Contains of all voters, where you go, registered voters who voted. Last time. Woo. So if I polled everybody and 80% of them said they voted, I feel pretty good that some of them have lied. There's a 4% chance I would be wrong, and if you want to get technical, that's a 2% chance I'm wrong, but I feel pretty good about that. Like somebody lied. No. Okay. So, now, any questions about those? Yes?
2B, we got 1425, but it was asking how many more students, so do we need to subtract it?
Oh, yeah, thank you. So again, if you stop here, you're fine. How many more students, technically, how many did I already talk to? 42. So yeah, you're right. So subtract 42 and you get 1383.
Yep.
So the real answer to how many more would be 1383 because you already talked to 42. But if you forgot to do that like I did, you're fine. I'm not going to take points off. But if you do a preliminary study, you've already got some data. Yes?
How are situations handled where there are more than two outcomes, like candidate A, candidate B, or not sure?
You could still do, so this is doing a confidence interval for the percentage, and for this case through voting, right? That Q hat would have not voted. You with me? So you could always do a confidence interval for each piece of something, because the P hat would be that thing, and the Q hat would have everything else. Now, to really answer your question, there is some stuff we might get into at the end of this class that deals with comparing more than two things at once. Those are called ANOVAs. We'll see how much time we have to do that at the end. Okay, so let's get into this one last piece of chapter 8. So just reminding us, we just did 8.1 and 8.3. We're going to go back and do 8.2 now. And the reason I do that is 8.1 and 8.3 still use this. And we know this. We know this, we've used it, we understand it, it's fantastic. 8.2 uses a different distribution. So you're going to get a whole new chart. Yay! Thanks, Jeff. But there's a very interesting history behind this thing. I want to talk a little bit about it. You guys can look it up yourselves if you're curious.